So we can sort of trivially see for n equals 0, right? Right, Fibonacci of 0 is going to equal 0, which equals, if we plug this into our formula here, we have phi to the n over square root of 5, or excuse me, phi to the 0, which equals 1 over radical 5. Is this the closest integer to 1 over radical 5? I think so, right? So this is approximate, actually, right? Yeah, 1 over radical 5, I'd say, runs down to 0. Is this useful for you guys? I haven't been paying attention to chat here. Yeah, for the case where n equals 1, right? We would also do Fibonacci sequence for 1, right? And then we're not raising phi to the 0th power, so we actually have to plug it in here, which would be, let's see, 1 minus radical 5, or excuse me, 1 plus radical 5 over 2 times, or over 2 radical 5, just to, and this ends up being, let me see if I can get my calculator out. Does anyone have the answer to what this evaluates to? Otherwise, I'll type it in here.
I think it's 3.618. I don't know if I did that right.
Oh, okay, here we go. So I got it. It's 0.7236. So dot dot dot. So that rounds up to 1. So far this makes sense. Yeah, oof, no worries if we're getting things wrong here. I'm definitely gonna get something wrong over the course of explaining this stuff. So I'm counting on you guys to call me out here as well. So yeah, so we have our base cases here. Let's see. So use induction in the definition of Fibonacci numbers to prove that the nth Let me see if I can shrink this down. Oh, nice, I can. Okay. So I'm gonna make this tiny, and I'm gonna zoom in because I want more room here. Let's see. Let me think here. So we have our base cases, and those seem to make sense. This holds for 0 and 1, right? And if I remember correctly, we know that. So so what I'm wondering here is, let's say we prove that the nth Fibonacci number is equal to phi to the n minus psi to the n over radical 5. And I saw a few people typing. Yeah, I could see how this this exercise would be a little annoying. It has also been a while since I've done these kinds of proofs. But for the sake of explaining it to you guys, I think I will simply look at the answer and then write it out in a way that will make sense. Oh, I see. Okay. Okay. That's not too bad, although it is going to take a little while to write out. So first we're going to prove that what it gave us in the hint, basically, that this Fibonacci of n is equal to this number, right? So maybe we'll erase these examples here. And we'll try this. So the base case where, excuse me here. So the base case where n equals 0 will have Fibonacci of 0 equals 0 equals 1 over radical 5, phi of 0 minus phi of 0, which 1 minus 1 equals 0. So this checks out. That's fine, right? N equals 1. First Fibonacci number, or for where n equals 1, the Fibonacci number is going to be 1, and then this is going to equal 1 over radical 5 of this expression, which if you expand it out, it'll be 1 plus radical 5 over 2 minus 1 minus radical 5 over 2 over radical 5, right? Which ends up being, let's see, we can simplify this down to so these are going to cancel. So 2 radical 5 over 2 5, which ends up equaling 1. So that makes sense. Okay, so now we have to consider the inductive case and prove that this holds for case where, you know, n, we're trying n equals, it'll make sense as I write it out. Sorry, here. So let's try the n plus 1th case, right? Which is going to be plus 1 minus 1 plus this, right? So these are the two previous numbers in the sequence. And if we write this out here in our expression, we're going to prove that this is equal to this here. Okay, so not too bad, right? And I think we can just plug in our old expressions here. We know that the nth Fibonacci number here is going to be 1 over radical 5. This resolves to n, by the way, is plus 1 minus 1. So it's going to be the same thing. And don't be too intimidated here by the Greek numbers. They're just so the number 5, it's because this is the Golding ratio is 1 plus radical 5 over 2. It's well, I actually won't get into it. Let's just get through this because it'll be a little while. How are we doing so far? Are we following what's going on here? Just cool. All right. So we're just plugging in here our expression and proving that for the n plus 1 case, this equality still holds, right? So then here, this is going to be 1 over radical 5, n minus 1 is n minus 1, which if we how would we resolve this algebraically? So I guess we can just move this 1 over radical 5 term here. And then we have, if we put like terms together, right? And then let's see, factor out the, I wonder if it would help to fully expand out this expression here. Maybe not. Let's try this. Extraneous parentheses here, but that, and then So actually, it does get a little easier if we rewrite this for the case where it's n plus 2, or rather, so let me write this out here in a way that follows what the solution is here, in case you guys want to consult it as well. Sorry, I still don't really know how to use this tablet. Apologies if I'm a bit of a boomer here, but so, we consider the inductive case, and I forgot that we have to introduce another variable. So let k be some natural number, right? So let's prove that this is valid.
I think it's screen sharing disabled.
Oh, is that working?
Yeah, perfect.
Cool. Prove that the equality is valid for n equals k plus 2. All right. So then, excuse me. So we have our two cases here, right? And I'll write these out again. Oh, excuse me, k plus 1. And so for k plus 2, we know that this is going to be the same thing. And we can rewrite k plus 2 in terms of the definition of the Fibonacci sequence, which would be, right, or the k plus 2 Fibonacci number in terms of its definition, right, which would be Fibonacci of k plus Fibonacci of k plus 1, right? And we substitute in these expressions here. And I think this is going to work here. Sorry, guys. Bear with me here 1 second. Okay. And then it's just a matter of algebraic manipulation here to get this equality, and we're going to get the same thing we got last time, just sort of in a different. Let me try rewriting this a little nicer. Phi of k times phi plus 1 minus phi of k phi minus 1. All this over radical 5. And let's see. Can we multiply this out? So the interesting part about this number psi here is that psi is the only solution to this expression where x squared equals x plus 1. That's kind of how we define the golden ratio here. So we know that this psi plus 1 is going to be all equivalent to psi squared. And I believe the same is going to hold for psi here, where, excuse me, psi minus 1 is psi squared. So in this case, we get the same expression here, psi plus 2 minus, or excuse me, yeah, 5 plus 2 minus psi k to the 2 over radical 5. And I can get into the golden ratio here, but I believe this is covered in the text of the book here. Let me see if I can find exactly where, here we go. So yeah, it's saying pretty much what I'm saying here. Psi approximately equal to 1.6180, and it satisfies this equation here of 5 plus 1 equals 5 squared. All right, so is this making sense so far? How are we doing? So to clarify, we've used the hint here that they gave us to prove that this expression here holds, right? That if I can scroll down here. So we've proven this, right? Now we need to prove that this is as close to the integer solution of, or is the closest integer to 5 to the n over radical 5, right? So for that, we basically need to prove that the difference between sorry, let me write it out here. So we need to prove that the difference between phi to the n over square root of 5 and this other expression here we need to prove that the absolute value of this difference is going to be less than 0.5 or 1/2 rather. Right. If this difference was greater than 1/2, then this would no longer be the closest integer, right? And to be clear, we've already proven that this is equivalent to the nth Fibonacci number. Does this make sense? This sort of game plan here. We proved the equality that they gave us, and now we're going to prove that that's the closest integer to this expression here, the phi to the n over radical 5, which let's see. So we can simplify this. Oop, did I lose the Okay, cool. Yeah, I don't have Discord Nitro, guys. Sorry. I, on principle, refuse to pay for it. It's already bad enough that I'm a Discord moderator. I'm really trying to tone down. But yeah, so this expression here, just simply, you know, algebraically, we can see that it simplifies down to this. Oop, the wrong thing here. So yeah, so this is what it simplifies down to. And we just have to prove that this is less than 1/2 for any n and any natural number. Right, so let's see. So let's plug in the actual definition here. We have 1 minus radical 5 over let's see, what was it? Over 2 over radical 5. And so this raised to the nth power. And again, it's just some algebraic manipulation here, where you can see that, well, this is going to be equal to 1 minus radical 5 to the n over 2 radical 5. And we know that any number less than 1 raised to some power is still going to be less than 1, unless the power is negative, I believe. So yeah, any number raised to some positive exponent is going to be smaller, right? In this case, 1 minus radical 5 is let me give you the exact number here. Oh, actually, this is negative 1.2 or 1.23606, etc. Let's see, what does this do here? So we know that radical 5 is less than 3. For reference, square root of 5 is equal to 2.23606, etc. It's an irrational number. And what it's telling us to do here is let me erase this here. This isn't helpful. Well, we know that 1 minus radical 5 over 2. This is going to equal the golden ratio, right? Or no, excuse me, this is different. This is the other one. Equals negative 0.61803, etc. Right. So we know that radical 5 is less than 3. 1 minus 5 over 2 is system 1. Right. And we'll have some negative components, but we don't care because we're looking at the absolute value here. Right. And so basically we know that roughly, well, not roughly, but we know that 1/3 is less than half. And we know that any number that we put here to some n power is going to be less than 1/2 if x to the n is less than, if this x to the n is less than 1, right? So let's see. And yeah, there's some more algebraic manipulation we can do to actually prove it exactly, but just from an intuition sense, and also because we've used 48 of the 50 or 48 of the 60 minutes allocated for office hours, I would say that, yeah, we proved it. QED, mission accomplished. Sorry if this wasn't, as useful as I set out to be, but that is how you would go about it. Yeah. So we can prove things about our programs here. I don't recall what the actual context was in the book. I know that we certainly implement some Fibonacci sequence, right? And we do it recursively. Well, I believe this was a way to introduce tail recursion. Yeah, here we go. Yeah, no, that was that is kind of tricky, and it would certainly be useful to look into these kinds of proofs and how they're done. I'm sure, yeah, like somebody mentioned the Khan Academy guy. I'm sure there are videos on how to do proofs by induction on Khan Academy and other sites, which I would encourage you guys to watch if you're interested in solving these kinds of problems. I promised you guys a watch party at 6, but if anyone else has any other problems that they'd like to go over, maybe in code, it'd be a little easier for me to solve those, I think.